In this lecture, we're going to look at a topic called energy diagrams. These are fundamental for us to understand organic processes, organic reactions, the energetics involved, and both looking at, it provides a way to kind of visually look at a reaction from both a thermodynamic and a kinetic perspective. So getting into it, again, we're going to talk about energy diagrams. And so energy diagrams allow us to visualize the energetics of chemical reactions. Okay, so what I want to do first is just kind of recap what we were looking at previously with thermodynamics. So in thermodynamics, we're looking at the balance of enthalpy and entropy and so balance of enthalpy, that was this thing called the delta H of reaction, or the delta H, the heat of reaction, if you will. But that's enthalpy. And then entropy, if it's the change in entropy, it's the delta S of reaction. Change in entropy. Okay, so we're looking at the balance of these two things, and really during a chemical process, as we go from starting materials to products, the changes in enthalpy and entropy will reflect the changes in stability. And another way of looking at stability is thinking about our energy term, potential energy. So potential energy, as things have more and more potential energy, it's like the bowling ball on top of the shelf, it is less and less stable. So that's why I like to use that word, stability, when I'm thinking about thermodynamics. Conversely, we want to also think about the kinetics of a chemical reaction. So kinetics are how fast a chemical reaction will proceed. And in upcoming lectures, we'll look at what influences whether or not a reaction will be fast or slow. These are really good ways of describing reactions. But all of these things, kind of the balance of enthalpy, entropy, and how fast a reaction occurs, can be easily depicted in what's called an energy diagram. And it's something we're going to be using quite a bit. It's a fairly simple graph. And so in an energy diagram, we have, first of all, let's just remind ourselves that this is a graph. So with a graph, and I'm about to run out of paper, but that's okay. With a graph, we have axes. We're going to consider only the positive y and positive x-axis. We're going to call this x-axis the reaction coordinate. The x-axis is called the reaction coordinate, and the y-axis is some sort of energy value. It's usually in kcals per mole, but let's not worry about the units of the energy. Let's worry about the type of energy that we're describing. So far, we've talked about kinetic energy, potential energy. We've broken chemical processes down into enthalpy and entropy. Here we're going to look at free energy, which takes into account both enthalpy and entropy as we're looking at sort of relative potential energies of chemical systems. And then what you typically get is a graph that looks like, that wasn't very smooth. Let's see if it's a little bit harder on the screen to make the cursor look smooth. But you typically get something that looks like this, and this is just a sort of typical shape. Okay, now let's break this down. So we have the coordinates of the reaction coordinate, excuse me, the energy diagram, that is reaction coordinate and free energy. And so I'm saying what we're going to have is we're going to have kind of a valley, a hill, and then a valley, and we're going to stop. Okay, so what we can do is we can break down this potential energy, we can break down this energy diagram by looking at the curve. Now the curve is called a potential energy surface. So we have this potential energy surface, and the potential energy surface has a few features that we want to pay attention to. First of all, it has the top of a hill. This is called a transition state. A transition state. And then we have these sort of bottoms of a valley. These are called ground states. Okay, so ground states. Let's kind of look in more detail at these various features of our potential energy surface, which is shown in our energy diagram. Let's start with the ground states. Ground states are, experimentally, they are, I'll rephrase that thought. They are chemical species that can be isolated. Now, in terms of what we've looked at in this class so far, ground states can be starting materials, products. So those two things we've looked at, what you start with and what you end up with in the midst of a reaction. We've seen those before. The thing we haven't seen yet is the idea of an intermediate. Okay, so an intermediate is something that's halfway between starting materials and products and can be what's called isolated. That is, we can actually put it, when I say isolated, that means we can actually put it in a bottle with some degree of success, maybe. It might not last very long, but we could certainly try to, in theory, put it in a bottle, isolate it from all of the other chemical species in the system. So this is sort of halfway between, a state halfway between starting materials and products that can be isolated. Okay, now the intermediate is going to feel a lot like this next feature of our potential energy surface. Again, the curve within our energy diagram, and that is the transition state. But there's a key difference. The transition state is, maybe a little bit more precise about this definition. Okay, so this is the arrangement of atoms and bonds where the system has sufficient energy to move to the next ground state. Okay, that's a fairly precise definition of the term transition state. I'm going to define it in a way that's going to make it a little bit easier to understand and wrap our heads around, but a little bit less precise, and it's going to start to look like the idea of the intermediate. So, said another way, with the transition state, it's where bonds are half, how about this? How about this? Bonds, where bonds that will break are sort of half broken. If you think about a covalent bond, if a chemical reaction is going to break a covalent bond, like the combustion reaction of octane that we were looking at, several covalent bonds actually break or rupture during that chemical process, and others are being formed, while others are being formed, okay? So in the transition state, the bonds that will break are half broken, and the bonds that will form are half formed, or partway formed to some degree. Okay, so this is kind of like if we have two ground states, Okay, maybe one's a little bit higher, one's a little bit lower, higher and lower ground states. The transition state is right between the two. And what's happening at the transition state is all of the bonds that will change, whether they're being broken or formed, are halfway between both of the ground states that are on either side of the transition state. In other words, and this is really bad way of kind of phrasing this given how I defined an intermediate, we're halfway between ground states. So if we were going directly from starting materials to products, you might say we're halfway between the starting material and products, and this is going to sound exactly like an intermediate. However, a transition state will connect a starting material to an intermediate, maybe an intermediate to another intermediate. It'll just connect ground states all day long. But one key difference between a transition state and an intermediate is this cannot be isolated. We cannot put a transition state into a bottle. We cannot isolate it. Okay. So what I want us to be able to do is kind of think in other ways about this. So the transition state is really powerful. Understanding the transition state is very powerful to understanding how a chemical reaction is occurring. The transition state has some features, okay? It's the top of a hill in a potential energy surface. Now the surface, so far, we're going to look at specific examples of these in the next lecture, but the surface so far looks something like this. This is the very top. That is our TS for transition state. Okay. What we say here is that generally bond formation and breaking are equal. Okay. And it's the highest energy a system can achieve before forming or transitioning to another ground state. Okay. So one key takeaway from this quick video would be if you had an energy diagram. Whoops. Okay. Would be to, if we have an energy diagram, we want to label the axes, label the ground states, and label the TS for transition state. Okay, so what that looks like is the axes are free energy, and if you got in the habit of writing this as kcals per mole, that's generally how we label our axes. Other parts of the world will use kilojoules. We can convert between either one just fine. Down here is reaction coordinate. And the very top of the hill is the transition state. One thing I'll mention just briefly about the reaction coordinate. This is a very vague coordinate, but all this is a vague kind of description of an axis in a graph. But all this is saying is this is how far along the reaction is. Okay, and that's it. All right, so in this quick video, we looked first, this is our first look into the world of energy diagrams. We're going to be using these extensively in the next few lectures, and we'll look at particular instances of chemical reactions, whether they're spontaneous, not spontaneous, exergonic, endergonic, that sort of thing, and draw various energy diagrams for them. And we'll also get a better understanding of things like intermediates versus transition states the more we use these things.